All right, class. Today we're going to talk about something that happens all around you, but you probably don't even notice it. Imagine you have a hot cup of tea sitting on your desk. You're not blowing on it, there's no fan, but slowly the tea cools down. Why? This happens because of something called natural convection. Natural convection means the fluid, like air or water, moves all by itself, without any help from fans or pumps. It moves just because of the temperature difference. Hot things heat up the air nearby, the air becomes lighter and rises up. Cold air then comes in to take its place. This makes a slow, invisible current around your hot tea, cooling it down naturally. Let's make it even simpler. Think about a hot boiled egg. You leave it on a plate, and after a while, it cools. How? The air touching the egg gets hot, becomes lighter, and floats up. The cold air from around comes in to replace it, and this repeats until your egg is cold. This is natural convection. If there was no gravity, like in space, this wouldn't happen, and the egg would cool very slowly. That's why astronauts need fans in space to cool things down, because natural convection doesn't work there. We also have something called the buoyancy force. It's just a fancy word for saying hot air goes up because it's lighter. This is the same reason why big steel ships can float in water. They push away water and float because the water pushes back up. In heat transfer, this push happens when hot air rises and cool air takes its place. To make things easy for engineers, we use numbers like the Grashof number. Think of it like a score that tells us how much the buoyancy effect matters. If the Grashof number is big, the hot air rises fast and we get stronger convection. If it's small, the movement is weak and slow. It's like comparing a big balloon rising quickly in the air to a small balloon barely moving. Now, heat can leave from many shapes, from flat walls, from pipes, from spheres like a hot ball, or even from finned surfaces like heat sinks in your computer. For each shape, engineers have made simple rules and formulas to know how fast heat goes away. For example, if you have a flat vertical wall, the heat goes away smoothly upwards. But if the wall is lying down, flat, it depends on whether the hot side is facing up or down. Hot side up means the hot air can escape easily, cooling it faster. Hot side down traps the hot air and slows down the cooling. Engineers also use something called the Nusselt number, which is like a grade on how good the surface is at throwing heat into the air. High Nusselt number means great at losing heat. We also use the Rayleigh number, which mixes the buoyancy force and how sticky the fluid is to predict if the air moves gently like syrup, laminar, or wildly like river rapids, turbulent. When you have fins, like metal plates attached to something hot, you can make cooling even better by giving more area for heat to escape. But if you put fins too close, the air can't flow properly, and you end up making things worse. There's actually a perfect gap between fins where heat transfer is maximum, and engineers can calculate it. Finally, sometimes you have both natural convection and forced convection, like a breeze blowing on your hot tea. When the wind is strong, forced convection is more important. When the wind is weak, natural convection dominates. Engineers compare these by looking at the Grashof number and Reynolds number. If the Grashof number wins, natural convection is king. If the Reynolds number wins, forced convection is more powerful. So next time you see steam rising from your coffee or feel the heat from your computer, you'll remember it's all because of natural convection. You'll also know engineers use simple numbers and formulas to design better cooling systems for everything from your laptop to power plants. And that's the fun world of heat moving around all by itself without fans or pumps.